Let's take a look at concavity in the second derivative test. So let's look at our first problem. And we've got y is equal to negative x to the third plus 5x squared minus 4. And the instructions say determine the open intervals in which the graph of the function is concave upward or concave downward. This is determining concavity. So determine concavity. Now concavity is where you got a graph where if I look at this part right here, see how it's opening down? So the graph is opening down. Then at a certain point, it changes and it's curved up. So the graph is opening up. This is concave up, this is concave down. Now the point where they change, wherever that might be, and this kind of looks like maybe right there, that's our point of inflection. And we'll see some problems in this section that will asking us to find the point of inflection. In business, that's also called the point of diminishing returns. And so if you got a problem that's asking you to find a point of diminishing returns, or asking you to find a point of inflection. If you look at like sales, you get your sales going like this. If this is DVD sales, you don't want to necessarily sell your company right here, because profits is leveled off completely, and it's going to start going down. So the rate of change has become very, very little here. At some point, the concavity will change. Let's say it's right there, and that's your point of diminishing returns. So your profit's still going up, but it's now the graph is curved down, which means it's starting to level off. Could be leveling off. It depends upon what your type of business is. DVD definitely would be leveling off. At this point, you can sell it. Somebody will buy it, and it's just like, whoa, why are they selling this? Profit's still going up. Up at this point, it's pretty obvious what's going on. So, but where do you sell in between here? That's more of what type of industry you're in, and what makes sense. It could be this curve right here is maybe anticipated to be a 20-year cycle. Something that changes really slow. Now, if you got technology, then that changes real fast. So, anyway, let's take a look at how to find concavity. Step 1. Determine the second derivative. Determine. Find the second derivative. Okay, so our first derivative, and that's kind of the hard part of this, find that second derivative. Now we're not talking about a polynomial, that's pretty easy. So y prime will be negative 3x squared. Take your power, put it out in front, lower it by 1. Here, take my power, put it out in front. 5 times 2 is 10, lower it by 1. And the number disappears. Then for a second derivative, take your power, put it up in front. Negative 3 times 2 is negative 6x. And we lowered it by 1. And then 10x just becomes 10. Step 2. Set the second derivative equal to 0. And solve. So we got negative 6x plus 10 equal to 0. And I'll take the negative 6x to the right side, so it becomes a positive 6x. Divide both sides by 6. And we get this, which would give us 5/3 equals x. Now this is our critical value. Some books call that critical number. That's where potentially the concavity is changing. Okay. Step 3. using the critical numbers, build a table of intervals pick test cases, plug into your second derivative, and simplify. Now, if our graph is concave up, then it's going to have a positive value. So concave up. If you come up with a negative number, then your graph will be concave down. Very similar to our figuring out where our graph is increasing and decreasing using the first derivative, we do the same thing here. We just look at the sign. Okay, so let's look at this one. So we got x is equal to 5/3. And I'll build a table of intervals. Now clear over here is positive infinity. Clear over here is negative infinity. We want to pick test cases. So I want to I want to pick a value between, I'll wake up yet. I want to pick a value between negative infinity and 5/3. 0 will be good. Now this is like 1 and 2/3, so 2 would be good, or 3. I'll do 3 just to make sure I'm beyond that. And then we want to plug those test cases into our second derivative. So plug into y double prime, which is negative 6x plus 10. So here's negative 6x plus 10. So I got negative 6. Negative 6 times 0 plus 10. And negative 6 times 3 plus 10. Well, negative 6 times 0 is 0, and that gives us 10. This is positive, so it's concave up. Now here I got negative 18 plus 10, which is negative 8. It's negative, so it's concave down. So for our intervals, it's concave up from negative infinity to 5/3, and then it's concave down from 5/3 to positive infinity. And those will be your answers. This is concavity and the second derivative test. So let me save this. Concavity and second derivative test. Page 01. There we go. And let's take a look at our second problem. Got y is equal to x squared plus 9 over 9 minus x squared. And instructions say determine open intervals in which graph the function is concave upward or concave downward. Well, again, our first step is to find our second derivative. Well, this has the quotient rule. This will be p and this will be q. P prime will be 2x. Q prime will be negative 2x. Our formula is p prime q minus p q prime over q squared. So for our first derivative, we got p prime, which is 2x, times q, which is 9 minus x squared, minus p, which is x squared plus 9, times q prime, which is negative 2x, over q squared, which is 9 minus x squared squared. And let me double check that. P prime q, okay, minus p q prime, that looks right. Now up on top, they both have a 2x, so I can factor the 2x out in front. Now here we're left with 9 minus x squared. Now over here, we got a negative negative, so that becomes a positive. The 2x is gone, so we got plus x squared plus 9 over 9 minus x squared squared. Negative x squared plus x squared cancels way up there. 9 plus 9 is 18 over this, which gives us 36x over 9 minus x squared squared. And that's our first derivative. Now let's find our second derivative. Quotient rule again. This will be p and this will be q. P prime will be 36. And q prime, this is the chain rule. We got parentheses to a power. So take power, put it out in front. What's inside the parentheses remains as is. Lower your power by 1, and then you multiply it times the derivative of what's inside the parentheses. Okay. So p prime, or p is equal to 36x, and q is equal to 9 minus x squared squared. And p prime we said was 36, and q prime. Simplify that a little bit. Or not simplify, but take a next step further. The derivative of 9 minus x squared is negative 2x. So we have 2 times 9 minus x squared times negative 2x, which gives us negative 4x 9 minus x squared. Okay, so now we're ready to plug in our formula. We got p prime q minus p q prime over q squared for a second derivative, or for our quotient rule, sorry. P prime was 36. Q is 9 minus x squared squared minus p, which is 36x, times q prime, which is negative 4x 9 minus x squared, over q squared, and q was 9 minus x squared squared, so we're going to square that. Now, I'll do a little bit of simplifying here. This is 36 times 9 minus x squared squared. Negative times a negative is positive. And I got 36 times 4, and x times x is x squared, and 9 minus x squared, over 9 minus x squared to the 4th power. Okay, so I didn't multiply these together because I want to factor out what they have in common on top. They both have a 36, so that comes out. And they both have 1 9 minus x squared. This first one actually had 2, and this just has 1 of them. Okay, so that 36 is gone. One of these 9 minus x squareds is gone, so we're left with 9 minus x squared. That 36 is gone. That 9 minus x squared is gone, so we're left with 4x squared here, over 9 minus x squared to the 4th power. Now this 9 minus x squared here cancels with one of these 9 minus x squareds. So this becomes 9 minus x squared to the 3rd power. And simplifying what's inside the brackets here, 4x squared minus x squared is 3x squared. There we go. 3x squared plus 9. And that's our second derivative. Okay, step 2. When we're finding the critical value of a fraction, what you want to do is you want to set your top part equal to 0 and your bottom part equal to 0. So we're going to take the 36 3x squared plus 9. Is that equal to 0? And we'll take the 9 minus x squared to the third power equal to 0. Now, these are going to give us our critical values. Now, realize that some of the values you get may not actually be valid in our original problem. Critical values may not exist here. That does not mean that doesn't indicate where the concavity is going might change. Over here, I'll drop 36, so I got 3x squared plus 9 equal to 0. Remember, if you have parentheses, something inside of parentheses to equal 0, and you got a number in front, you can just drop the number. We'll take the 9 over the right side, becomes a negative 9. Divide both sides by 3. Then we get x squared equals negative 3. Drop the squared and put a plus or minus square root around the other side. But a negative inside of a square root gives us an I, so I can just drop that piece. Now in this one I can drop third power, so we got 9 minus x squared equals 0. Take negative x squared to the right side, becomes a positive x squared. Drop the squared, put a plus or minus square root around the other side, and we get x is equal to plus or minus 3. And those are our critical values. Well, let's plug those into our table here of intervals. We got negative 3 and we got positive 3. And over here is positive infinity. And over here is negative infinity. And we want to pick test cases. So I want to pick a value between negative infinity and negative 3, like negative 4. Value between negative 3 and 3, like 0. And a value between 3 and positive infinity, like 4. And we want to plug into our second derivative now. So we'll plug that into our second derivative. All we care about is the sign. So our second derivative was 36, 3x squared plus 9. 36, 3x squared plus 9 over 9 minus x squared to the third power. So 9 minus x squared to the third power. Let's analyze this a little bit. 36 is positive. X squared becomes positive. Whenever you square something, it's positive. Positive times 3 is still positive, plus a positive 9 is positive, times a positive 36 is still positive. So I don't need to worry about the top part. It's going to be positive in all these. All I need to worry about is the bottom part. Okay, so let's plug negative 4 into the bottom. So we got 9 minus negative 4 squared to the third power. Okay, negative 4 squared is 16. 9 minus 16 is a negative number. A negative number to the third power is negative. So we got positive over negative, which is negative. So this is concave down. Now if I put 0 in, I got 9 minus 0 squared to the third power. 0 squared is 0. 9 minus 0 is positive. Positive number of the third power is positive. And positive divided by positive is positive. So this is positive. So it's concave up. Again, we could care less what the value is. We're just trying to figure out what the sign is. And if I put 4 in, got 9 minus 4 squared to the third. Well, 4 squared is 16. 9 minus 16 is a negative number. A negative number of the third power is negative. Positive divided by negative is negative. So this is concave down. So our answer is concave down from negative infinity to negative 3. Then it's concave up from negative 3 to 3. And then it's concave down from 3 to positive infinity. Let's go look at our original graph. So let's graph this. I'll press my y equals, press clear. Now when you're putting a fraction in, you have to put parentheses around top and parentheses around the bottom if there's more than a single number or a single variable. So I'll put a beginning parentheses, x squared plus 9. Close parentheses divided by beginning parentheses 9 minus x squared. Close parentheses and then graph. Okay, we said it's concave down from negative infinity to negative 3. Here's negative 3, and that definitely is curved down, isn't it? Then from negative 3 to 3, we said it's concave up. So negative 3 to 3, well, that's definitely curved up, isn't it? It's opening up. And then from 3 to positive infinity, it's concave down. It's opening down. So now you may not know how to find the concavity. You may be lost the derivative or so forth. But you'll know if you got the right answer. You just look at the graph, and you should be able to see if it looks reasonable. Let's save that. Yeah, let's look at the next problem. I don't know why it keeps flipping me out of that. Now this third example says discuss the concavity and find the points of inflection. So let's take a look at that. We got y is equal to x to the third minus 9x squared plus 12x minus 6. Now, we've already seen how to do the concavity. Step 1, find a second derivative. Step 2, set that equal to 0 and solve. Those are your critical values. Step 3, build a table of intervals, pick test cases, plug in your second derivative, and see what your sign is. So let's see how to find the points of inflection. Now, we don't have to do anything special to find the concavity. By finding points of inflection, we'll find a concavity, which we'll see. Now, remember, your points of inflection is where the concavity changes. So, first step. Find a second derivative. Not that I can't spell. Let's try it again. There we go. So y prime, take your power, put it out in front, so this becomes 3x squared, minus 9, take 2, put it out in front, so we got 18x, and then 12x becomes 12. And that gives us 6x minus 18. Step 2. Set the second derivative equal to 0. Set the second derivative equal to 0 and solve. So we got 6x minus 18 equal to 0. Take the negative 18 to the right side, becomes a positive 18. Divide both sides by 3. Well, divide both sides by 6, and we get 3. I shouldn't think of the answer. Now, these are our critical values. In this case, we only have one. Critical values, again, where something potentially happens, like concavity changes. Okay, so using the critical values, build a table of intervals. Pick test cases. Plug into your second derivative. And simplify. And if you come up with a positive, it's concave up. If you come up with a negative number, it's concave down. So let's do this one here. So we've got x is equal to 3. Build our table of intervals. This will be positive infinity. This is negative infinity. So for our test cases, we want to pick a x value between negative infinity and 3, like 0. And we want to pick one between 3 and positive infinity, like maybe 4. And we want to plug that into our second derivative, which was 6x minus 18. So I got 6 times 0 minus 18, which 6 times 0 is 0, minus 18 is a negative number, which means this is concave down. If I plug in 4 here, 6 times 4 is 24. 24 minus 18 is positive, so it's concave up. Again, I could care less what the actual value is. I'm just wondering what the sign is. Now, step 4. Assuming the x value is in our domain, it exists. So our graph exists at that point. Assuming the x value is in our domain, where the concavity changes, is your point of inflection, your POI. So for this one here, this is concave down and it changes to concave up. It changes to 3. If I come up here, 3 is okay up here. The only time you're going to have it where you have problems is potentially where you have radicals or where you have fractions. So plug the x value into the original function to find the y value. Okay, so we came up with x equals 3 is a point of inflection. So our original function was y is equal to x to the third minus 9x squared plus 12x minus 6. So plug 3 in. We got y is equal to 3 to the third minus 9 times 3 squared plus 12 times 3 minus 6. 3 to the third is 27 minus 3 squared is 9 times 9 is 81, so minus 81 plus 36 minus 6. 54? Negative 54? That looks right. 36 minus 6 is 30. And assuming I didn't make a basic math error, we would have negative 24 for y. So our point of inflection, and it's actually a point, so you have to find the y part, would be 3, negative 24. And that's how you find the point of inflections. Let me save that, and we'll look at another problem. Okay, let's look at this one. We got y is equal to x minus 2 to the third power and x minus 4. Well, step 1 is to find our second derivative. This is the product rule. We got something times something else, so this will be p and this will be q. Now this is a chain rule, so p prime, we take a power, put it out in front, we lower our power, or what's inside the parentheses remains as is, we lower our power by 1, and then we multiply times the derivative of what's inside the parentheses. Now the derivative of x minus 2 is 1, so that drops away. So we got 3 times x minus 2 squared. Now for q prime, the derivative of x minus 4 is 1. So our product rule, we got p prime q plus p q prime. So y prime, we said p prime was 3 times x minus 2 squared times q, which was x minus 4, plus p, which was x minus 2 to the third power, times q prime, which was 1. Now I've double checked that. P prime was right there. Q was this plus P, which is that, times Q prime. Okay. Well, let's factor out what they have in common. They both have an x minus 2 squared. This one has x minus 2 squared. This one has x minus 2 to the third power, so there's 3 of them. So here we're left with the 3 and the x minus 4. And over here, if I take away 2 of these, I'm just left with 1 of them. So I'm left with an x minus 2. So that gives us x minus 2 squared times 3x minus 12 plus x minus 2, which gives us x minus 2 squared times 3x plus x is 4x. Negative 12, negative 2 is negative 14. Now I'm going to factor out 2, because 4x and 14 have a 2 in common. I'll put it out in front here. So that gives us that, and this gives us 2x minus 7. And now we're ready for our second derivative. So, actually, let me leave that 2 alone out in front. So this is going to be our p, and this will be our q. So p prime, take your power, put it on front. What's inside of parentheses remains as is. Lower your power by 1, and then you multiply it times the derivative of what's inside of parentheses. So that just gives us 2 times x minus 2, because the derivative of x minus 2 is 1. And q prime will be, the derivative of 2x minus 7 is 2. Okay, so now we're ready to plug in our formula for our second derivative. Now we have this 2 out in front over here, so that's just going to be multiplied times everything. So we got 2, and then we'll put a big bracket times everything. P prime was 2 times x minus 2 times q, which was, what was q? 2x minus 7 plus p, which was x minus 2 squared, times q prime, which was 2. Let me scratch my eye here. There we go. Okay. Now this is our first group, and this is our second group. Why do I consider those groups? Everything's multiplication. 2 times x minus 2 times 2x minus 7. X minus 2 squared times 2. Well, these have a 2 in common, so that can come out in front. They also both have an x minus 2. Here's 1x minus 2, and here's 2x minus 2's. So I can bring 1 out. Okay, so that's 2's gone, that x minus 2's gone, so we're left with 2x minus 7. This 2's gone, one of these x minus 2's is gone, so we got x minus 2. 2 times 2 is 4, times x minus 2. And 2x plus x is 3x. Negative 7, negative 2 is negative 9. Now, 3x minus 9, they're both divisible by 3, so I can factor 3 out. So out in front here, we have 4 times 3 times x minus 2 times x minus 3, which gives us 12 times x minus 2 times x minus 3. Okay, step 2. Set this equal to 0 and solve. So 12 times x minus 2 times x minus 3 equal to 0. Now there's no need to set the 12 equal to 0, but the zero factor property from college algebra says if you get 0 on one side, you set each factor equal to 0. So I'll set x minus 2 equal to 0 and x minus 3 equal to 0. So we get 2 and we get 3. And these are our critical values. So let's build a table of intervals and see how it looks. So I got 2, I got 3. And clear over here is positive infinity. Clear over here is negative infinity. I will pick test cases. I will pick an x value between negative infinity and 2, like 0. I want to pick one between 2 and 3, like 2.5, which is 5 halves. And I want to pick one between 3 and infinity, like 4. Well, now we want to plug that into our second derivative. Second derivative is right here. So we got 12 times x minus 2 times x minus 3. Now again, I could care less about the actual value. I'm caring what sign is. So I got 12, and then 0 minus 2, and 0 minus 3. 12 is positive, so we can always ignore that. 0 minus 2 is negative, 0 minus 3 is negative, negative times negative is positive, so this is concave up. 5 halves. If I put 12, and then I got 5 halves minus 2, and 5 halves minus 3. Now remember, 5 halves is 2.5. Well, 2.5 minus 2 is positive. 2.5 minus 3 is negative. Positive times a negative is negative, so this is concave down. And if I plug 4 in, I got 4 minus 2, and then 4 minus 3. 4 minus 2 is positive, 4 minus 3 is positive, positive times positive is positive, so this is concave up. Which means on step 4, assuming our graph exists at 2 and 3, but if I go back to my original one, there's no fractions, there's no radicals. This is just a polynomial. So everything exists there. So that means our point of inflection is where the concavity changes. Well, it changes here. It's concave up to concave down. So one POI is at 2. And we have another POI over here. This is concave down, changes to concave up. So it'll be at x is equal to 3. Now we want to plug these values into our original function here. So we've got y is equal to x minus 2 to the third, x minus 4, and same thing here, x minus 2 to the third, and x minus 4. Well, if we plug those in, we're going to get 2 minus 2 to the third, and 2 minus 4. Well, 2 minus 2 is 0. 0 to the third is 0. 0 times anything is 0. So this POI is going to be at 2, 0. This one, if I plug 3 in, I get 3 minus 2 to the third times 3 minus 4. 3 minus 2 is 1. 1 to the third is 1. And 3 minus 4 is negative 1. So that gives us negative 1. So we'll have a POI at 3, negative 1. Let's graph this. See what it looks like. So press y equals, press clear, x minus 2 to the third, so beginning parentheses, x minus 2, close parentheses, caret 3, beginning parentheses, x minus 4, closing parentheses, then graph. POI is 2, 0. 2, I can kind of see that. This looks like it's concave up here, then changes to concave down, and then 3, negative 1. 3, negative 1, yeah, I can see that too. So sometimes if your numbers are small enough, like this right here, you can actually look at your graph and see it. I think the previous one, it would have been, we would have had to zoom, and it would have been hard to see. But definitely if you got this, you can eyeball it and check to see if you did right. So let me save this. And let's look at our next problem. It says discuss concavity of the graph and find the points of inflection. Again, we have to find a concavity to determine the points of inflection. First step, we want to find the derivative, or second derivative. Sorry, let's think about something else. This will be p, and this will be q. So we need p prime, which would be 1, and then derivative of x plus 2 is 1. Okay, so let's plug this into our formula. So it's p prime q minus p q prime over q squared. Well, p prime we said was 1 times q, which was x plus 2, minus p, which was x minus 1, times q prime, which was 1, over q squared. So we got x plus 2 squared. That gives us x plus 2. Remember, a minus out in front flips the sign of everything inside. So the positive x becomes a negative x. The negative 1 becomes a positive 1. Over x plus 2 squared. Now x minus x drops away, so that's gone. 2 plus 1 is 3. Over x plus 2 squared. Now I could actually rewrite this as 3 times x plus 2 to the negative 2 power. If you got something to a power, you take it opposite where it's at in a fraction, and sign of the exponent changes. And now to find our second derivative, we can use the chain rule. Take a power, put it out in front. What's inside the parentheses remains as is. Lower your power by 1, so negative 2 minus 1 is negative 3, times the derivative of what's inside the parentheses. Okay, so that gives us negative 6, x plus 2 to the negative 3 power. Derivative of x plus 2 is 1, so that drops away. Put negative 6 up here. X plus 2 to the negative 3, we're going to take that down below. Anytime you have a negative exponent, you can take it opposite where it's at in a fraction, sign of the exponent changes. And that's our second derivative. Step 2. Set the top part equal to 0, set the bottom part equal to 0. So we got negative 6 equals 0, and x plus 2 to the third power equal to 0. Now negative 6 equals 0, I don't need to worry about that. There's no x to solve for. Over here, remember, if you have parentheses to a power equals 0, you can drop the power. So we just set the x plus 2 equal to 0. And we get x is equal to negative 2. So this is our critical value. So let's plug that in. So I got x equals negative 2. Over here is positive infinity. Over here is negative infinity. We want to pick our test cases. Some value between negative infinity and negative 2, like negative 3. Some value between negative 2 and infinity, like 0. And we want to plug this into our second derivative. So our second derivative was negative 6 over x plus 2 to the third. Okay. Again, all we care about is the sign. We don't care about anything else. So we got negative 6 over negative 3 plus 2 to the third. Well, negative 3 plus 2 is negative 1. Negative 1 to the third is negative. Negative divided by negative is positive. So this is concave up. So it's concave up from negative infinity to negative 2. Now here I plug 0 in. So we've got 0 plus 2 to the third. 0 plus 2 is 2. 2 to the third is 8, which is positive. Negative divided by positive is negative, so this is concave down. Now step 4. Our concavity changes here, but let's go check if a negative 2 exists in our original function. If I put negative 2 in for x, I get negative 2 plus 2 in the denominator, which we can't have. So negative 2 doesn't actually exist. It's not in our domain, which means there's no POIs. I mean, definitely the concavity changes, but it can't have a point of inflection if it doesn't exist at that point. Now, if you don't remember that and you go through and you try to plug it back in the original problem, you'll get something that's undefined. So it'll be obvious. Let's save this. Yeah, let's look at our next problem. So we got y equals 2x to the third plus 3x squared minus 36x plus 12. And it says find all relative extrema, use the second derivative test. So find the relative extrema using the second derivative test. We'll be talking in a second about, or not a second, but we'll be talking about the second derivative test here in a little bit. So let's take a look at the steps for using this. Step 1. Find the first derivative. Okay, so y prime would equal to 6x squared plus 6x minus 36. Set equal to 0. And solve. So we got 6x squared plus 6x minus 36 equal to 0. Now, since this is an equation and everything's divisible by 6, I could go through and divide everything by 6. So that would give us x squared plus x minus 36 divided by 6 is 6 equals 0. That gives us x plus 3 times x minus 2 equal to 0. And set each one of those equal to 0. So we got x plus 3 equal to 0 and x minus 2 equal to 0. And we get x is equal to negative 3 and x is equal to positive 2. These are our critical values. Third step. Find the second derivative. So continuing from where the first step left off, that gives us 12x plus 6. Now 4. This is a second derivative test here. Plug each critical value into the second derivative. Now really notice what we're doing here. Those critical values came from the first derivative, didn't they? And then we're plugging them into the second derivative. So plug each critical value into the second derivative and simplify. Now if it's positive, that means that that critical value is a min. So if it's positive, critical value is a min. If it's negative, the critical value is a max. a relative max. If it's equal to 0, it fails. Do what you did before. What you did before? Well, what we did before is we found a first derivative, set it equal to 0, solved that, found our critical values, built a table of intervals based upon our critical values, picked test cases, looked at our sign to see if it's increasing or decreasing, and from there found our min and max. Okay, so for this one, our critical values were -3 and +2. So I'm plug those in my second derivative. So I got 12 times -3 plus 6, which gives us -36 plus 6, which is negative, isn't it? Again, I don't care what the value is, but it's negative, which means that at -3 is a relative max. Now do the same thing for 2. I'll plug 2 into my second derivative. So I got 12 times 2 plus 6. 12 times 2 is 24. 24 plus 6 is positive, which means that at x equals 2 is a min. Now, just like before, we still have to find our y values. So here, I'm going to take -3, plug it back into my original function, whatever that said. Wow, that's nasty. Okay, 2x to the third plus 3x squared minus 36x plus 12. So plug -3 in there. We got 2 times -3 to the third plus 3 times -3 squared minus 36 times -3 plus 12. -3 to the third is -27 times 2 is -54. -3 squared is 9 times 3 is 27 plus 108 plus 12, which gives us -27 plus 120, which gives us 93, I believe. Minus any math errors I might have made there, adding, subtracting, so forth. Plug that in your calculator to verify what it is correct, but we'll pretend I can actually multiply and add numbers. Okay, so we got relative max at -3, 93. Now over here, I'm going to plug the 2 in. So we got 2x to the third plus 3x squared minus 36x plus 12. And plug the 2 in. So we got 2 to the third plus 3 times 2 squared minus 36 times 2 plus 12. 2, 4, 8, 16 plus 2, 4, 12 minus 72 plus 12. 12 plus 12 is 24, 40 minus 72, which gives us -32, I believe. Which means we'll have a relative min at 2, -32. Okay, second derivative test. I don't like it. I don't emphasize it very much in my classes. Usually finding a second derivative is not a very nice option. Unless you give the person a very simple problem to begin with, like a polynomial, like this one right here. Then it works out fairly nice. So I don't like it for that reason. Second derivative oftentimes is very difficult to find. And once you get your first derivative, it's not that hard to build a table of intervals and test cases anyway. Second reason I don't really care for it. Now, there are times when this is beneficial, but the second reason why I don't care for it for the average student to use is it doesn't always work. If you got 0 here instead of a negative number or positive number, it fails, and you have to go back and do whatever you were doing before anyway. So again, I don't care for it that much. But I'd be remiss if I didn't actually show you an example. It's not a hard concept. It just, well, yeah, it is. One more line. Find that second derivative can be hideous sometimes. I like how it just randomly throws me into this page or that page. We're done with that, so let me stop the recorder. Go back here. Concavity and a second derivative test.